In our previous lesson on efficiency, we learned that a lot of machines are not as efficient as you would think. It's not uncommon for, most or a lot of the energy you put into a machine to not really come out the other side or to not be used to achieve the goal of the machine. A lot of the energy ends up seemingly disappearing. But we know from the law of conservation of energy that energy can't just disappear. It can be transferred to another object or to another form, but it can't be destroyed. It can't go away. So whenever we have a machine that seems inefficient, that seems like it's losing some of our energy, we need to ask ourselves, well, where is that energy going? And more often than not, the answer is that the energy is going to heat. A lot of machines create heat as sort of a side effect or as a byproduct, even though we might not necessarily want them to. A great example would be a car engine. The purpose of a car engine is to make your car go, to give your car kinetic energy. But if you touch a car engine that's been running for a while, you find that they're very, very hot. So even though we don't really want car engines to be hot, the goal isn't to heat the air around it. It's sort of a side effect. And a lot of the energy that goes into the car engine in the form of chemical energy in gasoline comes out not as kinetic energy that your car has, which is what we would want, but comes. This sort of provides a good segue into a lesson on thermal energy and on heat. Now, to talk about thermal energy and heat, we should first talk a little bit about temperature. And some of the things I'm going to say here are things you probably know about temperature, but hopefully I'm going to introduce you to some new ideas as well. So the units of temperature are degrees Celsius, or more commonly in physics, we use a unit for temperature called Kelvin. This is Kelvin with a capital K, because again, like a lot of our units in physics, it's named after a person, named after Lord Kelvin. So what you need to know about Kelvin is a change of 1 Kelvin is equivalent to a change of 1 degree Celsius. So if you have some water sitting on your stove and you heat it up by 1 degree Celsius, you've heated it up by 1 Kelvin. If you heat it up by 10 degrees Celsius, you've heated it up by 10 Kelvin. So then students often ask at this point, well, aren't they just identical? Why do we have to have 2 different scales? Although the Kelvin scale and the Celsius scale are sort of split into equally sized pieces, they start at totally different places. So that water on your stove might have started out at a temperature of 20 degrees Celsius. But the temperature it started out at in Kelvin would have been hundreds of Kelvin. So these are very two similar scales in that a change of 1 Kelvin is the same as a change of 1 Celsius, but they start at very different positions. So some key temperatures. 0 Kelvin is minus 273.15 degrees Celsius. Now, at first glance, this seems like kind of an arbitrary number, but it was picked very specifically. There's something important that happens at this temperature. Now, you might recall that temperature comes from the movement of molecules. Every object, every piece of matter is made up of molecules, and those molecules are moving back and forth. And if it has a lot of temperature, they're moving back and forth a lot, very quickly. If it has not much temperature, they're moving a little bit more slowly. They're not moving as much. So if you can imagine cooling that object down as cold as you possibly can, those molecules are moving slower and slower and less and less. Eventually, those molecules would come to a stop. And at that point, you could not possibly cool it anymore. You can't move less than not moving at all. That temperature is negative 273.15 degrees Celsius, and that is the temperature we've referred to as 0 Kelvin. You also hear this temperature referred to as absolute zero, meaning it is absolutely the definition of no temperature whatsoever. You can't have less temperature than absolute zero. So from a physics perspective, it's actually a pretty smart, sensible place to start counting Kelvin. So 0 Kelvin is when molecules have stopped moving, and it's equivalent to negative 273.15 degrees Celsius. So 0 degrees Celsius ends up being the same as positive 273.15 Kelvin. And 100 degrees Celsius, which is a common one we think about because it's the temperature at which water boils, is going to be 373.15 Kelvin. So to get from this in degrees Celsius to this in degrees Celsius, I have a jump of 273.15 from there to there. So my jump in Kelvin is going to be the same, from 0 to 273.15. And to go from here, 0 Celsius, to here, 100 Celsius, that's a change of 100. So to go from the equivalent temperature in Kelvin up to here, I would also need a change of 100 Kelvin. So a change of 100 Celsius is a change of 100 Kelvin, but the absolute values are very different. OK, on to thermal energy itself. Thermal energy is energy contained within an object as a result of its temperature. This thermal energy comes from all the kinetic energy of all the molecules in the object. So you can remember we were just talking about how every single piece of matter is made up of molecules that are moving back and forth. And each of those molecules will have some kinetic energy. Right? Kinetic energy 1/2 mv squared. So as long as that molecule has some mass and it has some speed, it will have some kinetic energy. And if I take the kinetic energy of one of those molecules and the kinetic energy of another molecule and the kinetic energy of a third molecule, and I go through all the molecules in the object and I add all of their kinetic energies together, that would give me basically the temperature of that object. So thermal energy is really just kinetic energy, but it's kinetic energy on a microscopic level. It's been all added together. So this means if I want to increase the thermal energy of an object, I can do so in two ways. Because thermal energy is just kinetic energy, 1/2 mv squared, I can increase it by increasing the temperature, which is basically like increasing v, the speed at which the molecules are moving back and forth. Or I can increase the mass, m. So if I have a pot of water sitting on my stove, 20 degrees Celsius, there's two ways I can increase the amount of thermal energy in the water in that pot. I can increase its temperature, which is basically increasing the speed of all the molecules in it. Or I can just add some more water to the pot. Even though that maybe doesn't increase its temperature, it increases the mass, how many molecules there are. And they might all be moving at the same speed they were before, but now I have more of them. I have more m. So that would increase the kinetic energy and the temperature. This one is usually pretty obvious to people. Heating something up gives it more thermal energy. This one's a little more subtle. Simply having more of something gives it more thermal energy. When thermal energy is transferred between objects, we call it heat. I'm going to be kind of particular here. We often use the words heat, thermal energy, temperature interchangeably in everyday language. But in physics, they all have very specific meanings. Thermal energy is different from temperature, and it's different from heat. They are three different things. OK, now let's look at an equation for heat. Q equals mc delta T. So what do all these symbols represent? Well, Q is heat. M is mass. Delta T is the change in temperature. And C is this new letter we haven't used before. C is called the specific heat capacity. And this will be a different number for different materials. So what this equation basically says is that if I have an object with a certain mass and a certain specific heat capacity, think of this as like the ability of the object to take in thermal energy without getting too much hotter. So I have an object with a certain mass and a certain capacity for taking in heat. If I add some heat to it, it's going to change its temperature. So the more heat you add to an object, the more its temperature changes. The more the object's temperature changes, the more heat must have been added. So let's talk units here. Well, Q is heat, which is the transfer of thermal energy. You might recall that we've talked about transfer of energy a lot in this unit. And the transfer of energy is also referred to as work. And work and all types of energy are measured in joules. So heat, transfer of energy, is also going to be measured in joules. Mass, as usual, is going to be in kilograms. Temperature, we're going to measure in Kelvin. Although, because this is the change in temperature, you can measure this in Celsius too, and you'll still get the same answer, because a change of 1 Celsius is the same as a change of 1 Kelvin. Now, the units for heat capacity, we could sort out by doing a little bit of algebra. If I want to isolate C, keep it on this side of the equation all by itself, I'd move M over to this side on the bottom of a fraction, and I'd move the delta T over to this side on the bottom of a fraction. So I'd have Q on top and M and delta T on the bottom, which means my units of C are going to be the units of Q on the top and the units of M and delta T on the bottom. And indeed, C is in joules divided by kilogram Kelvin. There's a few different ways you'll probably see this unit pronounced or hear it pronounced. Often the way people pronounce it is just sort of the way it looks. They say joules per kilogram Kelvin. But sometimes people are specific about the fact that, well, because kilogram and Kelvin are both on the bottom, we're dividing by both of them. So we should really incorporate that into our pronunciation of the unit. And they'll say joules per kilogram per Kelvin. Kind of like the way we say meters per second sometimes for the unit of acceleration. Anyways, you'll hear this pronounced both ways, and both of them are fine. So what are some heat capacities of some common materials? Well, water, which is one we've talked about already, has a heat capacity of 4,180 joules per kilogram Kelvin. Carbon, common element, 720 joules per kilogram Kelvin. Iron, 460 joules per kilogram Kelvin. Copper, 390 joules per kilogram Kelvin, and lead, 130 joules per kilogram Kelvin. I sort of arranged these in descending order. So what this means, because water has a very large heat capacity, it means without changing its temperature too much, water can take in a lot of heat. It has a capacity to hold a lot of heat. This basically means, one way you can think about this, if you had 1 kilogram of water and you raised it 1 Kelvin in temperature, that would require 4,180 joules. So a lot of energy, and it only went up 1 Kelvin. Lead, on the other hand, if you had 1 kilogram of lead and you wanted to raise it 1 Kelvin, that would only require 130 joules, 130 joules per kilogram per Kelvin. So it's a lot easier to heat up lead than it is to heat up water, because water has the ability, it has the capacity to hold a lot of that heat in without increasing its temperature. Keep these values handy, because you'll probably have to refer back to these when you're solving problems in the future. Now, there's one more tidbit I need to give you before we start solving problems to do with thermal energy and heat. And that's that when two objects are in contact, heat is transferred from the warmer object to the cooler object. That should be fairly obvious, until they've reached what we call thermal equilibrium, which is a fancy way of saying they have the same temperature. So two objects, different temperatures, they touch each other. Heat is going to go from the warmer object to the cooler object. Remember, heat is the transfer of thermal energy. And that transfer is going to keep going until the objects are the same temperature. And then there's no reason for energy to go one way or the other. So let's try solving a problem. A 35 kilogram child goes down a 3.2 meter high slide. The child is initially at rest and is moving 1.8 meters per second at the bottom of the slide. The slide is made of 12 kilograms of iron and all the heat is transferred into the slide. How much does the temperature of the slide increase? So for starters, let's just focus on this first part of the problem here. This seems very much like a conservation of energy problem. I know the mass and the height of the child to start with. He's got some potential energy. Then they go down a slide and end up with a speed at the end, so he has some kinetic energy. So let's see what applying the conservation of energy law to this first part of the problem. Let's see where it gets us. So here's our conservation of energy equation. To start off with, the object has some energy. Then some work is done on it, meaning that energy is maybe transferred to or from other objects or to or from other forms. And it has some leftover energy at the end. Now, in the case of this child, initially at the top of the slide, he is at rest, so no kinetic energy. He does have some potential energy because he has some height, and that is expressed in this formula here. As he goes down the slide, there's maybe some work done by forces other than gravity, which we accounted for here. There's probably some friction acting on this child as he slides down the slide, and friction can do work on him. So we don't know what that work is, but we'll leave it here in the equation for now. At the end of the slide, when he's at the bottom, now he has no more height, so his potential energy final is 0, but he does have some speed. So we have kinetic energy expressed by this formula here. So next step, let's fill in what we can. This is the mass, little g, and the height of the child at the beginning, top of the slide. So those numbers go in here. This is the mass of the child and the speed of the child at the end, final. Those numbers go in here. Then I can crunch that in my calculator and solve for the work done by other forces, and I get it's negative 1040.9 joules. Now, negative work, you might need a bit of a reminder as to why this might be negative and what that means. And that's coming up in a second. But first of all, let's just remind ourselves what work actually is. Remember that work is energy that's being transferred to another object or to another type of energy. So as the child went down the slide from initial to final, there was some work. There was some energy being transferred. So some energy has left the child, right? They have less energy final than they did initial, and it's gone to some other object. The work in this problem is negative because the child was losing energy and because friction was in a direction opposite to the child's motion. Remember that when the force and the distance are anti-parallel, work is negative. So there's a couple of reasons why you should kind of buy that this work should be negative. The child is losing energy, so energy is being taken away from him, transferred away from him. So that's one reason you can think about this work being negative. And also because the work is being done by friction, and friction is opposing the child's motion. That's the other convincing reason why work should be negative here. So we have this child going down a slide. We know that energy is getting taken away from the child by friction, but that energy can't be destroyed. It needs to go somewhere else. And where it's going to go to is the slide. And it says here that heat is transferred into the slide. So where is this work transferring the energy to? To the slide in the form of thermal energy. So that's going to bring us to the second part of the question. We now know that this much energy has gone into the slide and become thermal energy. So that should let us figure out how much does the temperature of the slide increase. We know the amount of energy that's been added to it. How much should that increase the slide's temperature by? Well, here's where today's equation comes in. Q equals mc delta T. This is the heat that goes into the slide, the energy that's transferred into the slide. So this is our number from before, that negative 1040.9 joules. That's the energy that goes into the slide in the form of heat. M is going to be the mass of the slide. C is the heat capacity of the slide. Again, this will just depend on the material the slide is made out of. And this delta T is the thing we're looking for. That's how much the slide's temperature changes by. So Q is going to be 1040.9. It was negative up here because we were talking about the child, and that energy was leaving the child. But because that energy is going into the slide, it's positive when we're talking about the slide. The mass of the slide was 10 kilograms. C, the heat capacity, well, the slide was made of iron. And we said before that iron had a heat capacity of 460 joules per kilogram Kelvin. So that's where this 460 comes from. And there's our delta T, the change in temperature of the slide. And we can solve that. We get the delta T equals 0.19 degrees Celsius or 0.19 Kelvin. So someone watching this child might say, hey, seems like energy has disappeared here. The kid had all this potential energy at the top. He had a bit of kinetic energy at the bottom, but it was less than he started with. Was the energy destroyed? No, it wasn't destroyed. It was just transferred to another object, to the slide, and to another form, to thermal energy. And you can notice that by measuring the temperature of the slide, and you'd see that it was 0.19 degrees warmer.